All right. Today we want to talk about Euler's law of motion and angular momentum. So in order to do that, we need two things to derive first. So imagine that you have a rigid body. Then uh, let's say we have a coordinate system at OU. And then I select a point C on the rigid body and another point, let's call it I on the rigid body. All right. Then I can write the location vector of C by RC, this one by RI, and this one, let's use small ri, all right? Then I can write, just regular vector addition that Ri equals to RC plus Ri. Then when I do one-time derivative, this derivative of this would be vi, the velocity, equals to the derivative of this would be the velocity of point C, and Ri, the derivative of this, because Ri, the magnitude of that Ri is not changing, but the rotation is changing because this rigid body is rotating. So it is not necessarily, I mean, having translational motion, it might rotate as well. So this Ri has is changing in time because the orientation of that is changing, and that would equal to omega cross Ri. So if I attach a coordinate system to the rigid body at C, for example, let's say I build a coordinate system here, then that coordinate system, I can measure omega for that coordinate system, how that coordinate system is rotating. Then the change of Ri would be omega cross Ri. There is another video explaining this, why rotation matrices become vector cross product. So you can watch that video. But if you can accept that, okay, the rate of the change of Ri would be omega cross Ri, we can move forward. And we get acceleration, one more time derivative, I, keep it that way, I equals to AC plus this cross product, the derivative of that is like derivative of the regular product, right? You would have product rule, derivative of this times this times derivative of that. The same thing for cross product. So I would have derivative of this, which is alpha, derivative of angular velocity is angular acceleration cross Ri plus this cross derivative of that. And derivative of this is, we already did it, it is omega cross Ri, all right? Now, one other thing, this is relative velocity of I with respect to C. Because you see, we have velocity of I equals velocity of C plus that relative velocity, right? So this is that relative velocity. So keep these. Then the other thing is about center of mass. Let's say I have a mass M1, and then I have another mass M2, which is bigger. Then the x coordinate of M1, let's call this x1. The x coordinate of M2, let's call this X2. Then the X coordinate of the center of mass, which would be somewhere closer to the bigger mass, right? X of M, X of G, center of mass, equals to M1 X1 plus M2 X2 divided by M1 plus M2. So if I have a bunch of other masses, I would keep going. So I would have, for example, M1 X1 plus M2 X2 plus M3 X3 plus M4 X4 divided by M1 plus M2 plus M3 plus M4. This is like weighted average, right? So now that we can write this for X, we can write the same thing for YG, right? Then rather than having that this way, I bring this masses and I call this total mass, capital M. So M1 plus M2 plus all of them, I call it total M equals to, instead of M1, X1, M2, X2, M3, X3, I just write it as summation of MI X, sorry, MI Y. We are talking about Y now. MI YI. And we do this summation over I. Now we can write the same thing for Z coordinate of Y, Z coordinate of the center of gravity. So MZG equals to that. So we have it for X, Y, and Z. So we can write it as a vector sign R of G equals to sigma of all point masses MI RI. This is a vector equation. So it has X component, Y component, and Z component. X component would be this, Y component would be this, and Z component would be similar to that. So any vector equation in 3D is in fact three components, three equations, right? So now that we have these, so let's move on to the next section. Imagine again that I have a rigid body. And I have point C, like before, and I have point I, like before. And now, this point I would have some velocity. Vi with respect to C, it would have some relative velocity. I want to find the moment of this relative velocity times mass, which becomes linear momentum of that with respect to C. I want to find the moment of the linear momentum. So think about rigid body as a lot of infinitely many point masses that are connected to each other and make something that it is rigid, meaning that the distance between 2 points, the distance wouldn't change. The vector is changing, but they don't get closer or further away for a rigid body, all right? So now that we have that I, so let's say that G is also here. The center of mass is somewhere here. So I would write this Ri, right? I would do the moment of this relative velocity times mass, which is linear momentum relative to C. So I would write it as Ri cross product with Mi Vi with respect to that C. And I sum it over I. This I call H. Let's erase this and make some room for H here. So let's call this H of C. And that is a vector. So I sum over relative velocity times mass, linear momentum relative to C, and moment of that. So I call this angular momentum around point C. Moment of linear momentum relative with relative velocity. So this is angular momentum around point C. Now let's see how that would change in time. What is the derivative of that? Derivative of that would be, again, summation over I. Derivative of this, which is like before, we have derivative of that would be omega cross Ri cross Mi, and Vic, I write it as, again, omega cross Ri plus, I just did the derivative of this term. Then I have to do the derivative of that term. Derivative of this term, which is derivative of this, is these two terms, right? Derivative of this became these two terms. I write the derivative as AI minus AC, because AI minus AC becomes these two terms. So I write it as Ri cross Mi AI minus AC. This whole thing is inside this summation. Now this is zero. Why? Because this is a scalar. This is some number. This is a vector cross a vector multiplied by a number. Cross product of any vector with some vector which is aligned with that. Maybe it is multiplied by 2, by half, by 3, by whatever. It is on top of that. So the sign of angle between them would be zero, because remember, the cross product would be the magnitude of the cross product would be the magnitude of the first one, magnitude of the second one, times the sign of angle between them. So the sign of angle between this and this is zero. So this term vanishes. So I have just these terms. Now, if I write this again, we can simplify it a little bit further. It is summation over I. Ri, let's make it into two summation. Ri cross Mi Ai minus Ri cross Mi AC. Now, you see, this AC is constant. It comes out of this sigma. It's like I'm adding bunch of things, and I can factor out that AC. It is a common factor in the summation. So I can factor it out and bring it out of the integral. And this, I can use Newton's second law and write it as all the F's forces that it is applied on that I. So I can write this as sigma I Ri cross Fi MIAI becomes F, the forces, the total forces at I, minus, now I have Ri MI. This is a number, right? I can bring this in front of that one. So it would be MI Ri remember MIRI would be MIRI, the sum of that would be MRG, right? And we're talking RI, we put our origin this time at C. So let's call it RG with respect to C. So instead of that, I can write it as, instead of summation, I can write it as MRG with respect to C cross AC. Now we want to simplify this term. So let's discuss it. For any point, let's use this side of the whiteboard. All right, so let's look at this term, all the forces on Fi. So if I have 2 points on a rigid body, let's say again on a rigid body, if I have 2 points, I and J, then first of all, for each point, I can say that there are two types of forces, internal forces and external forces. So let's call this F external at I. Then, and my point C is here. Then for internal forces, I call this Fi from J, all right? So in the summation, I would have internal and external forces. For internal forces, for each Fij, I would have the opposite force. So again, let's bring this let's plot this I and J outside for clarity. So if I have some force that way, there is another force the same magnitude in the opposite direction. That it is, if this force is on I from J, then the opposite of that should be on J from I. So this is on J from I, and this is on I from J. So if I look at the terms that has that, it would be Ri cross Fij. So for each Fij in the summation, I should have Fji and Rj. So in summation, I would have this term as well. So they should come in pair. Why? Again, third law of Newton. Because for each Fij, for each one of those internal forces, I would have the opposite of that. I mean, I would have the same thing in the opposite direction, right? But for external forces, that is not the case. For external forces, we might have that thing, and this would apply that on another rigid body, not inside the rigid body. So this, if external, this would push back on that other object. But we are talking about inside the rigid body. So they should come in pair. Now, this is negative of this. So I can say that's negative of Fij, then factor out Fij. So I would be left with Ri minus Rj cross Fij. Ri minus Rj, you see, let's say this is point C, this is Ri, and this is Rj. Minus of that would be this. So I would have this vector and this vector. So this is Ri from point C to I, it would be Ri. And this is Rj, but negative of that would be this one. So it is this plus this. So it would be Rji. So this would be Rji. So it is the vector that goes to I from J. So it is Rji. This cross that for all mechanical forces, when we have 2-point masses, are zero. Because we have cross product, this would be that line, and all the forces between 2-point masses in mechanical cases are zero. You might ask that if there are 2 electrons, then we might have still third law of Newton, opposite forces, the same magnitude, but they are not in the same line. They are not on this line, you see, on the line connecting these 2 electrons. Well, that is true, but still it holds true. The angular momentum, we can, have similar thing. And that is not the topic of our discussion here. We are talking about mechanical system, but rest assured that that wouldn't cause anything about conservation of angular momentum and so on and so forth. So even that is true for um, electromagnetic forces. But in those cases, we talk about angular momentum for a field, not something like this. So for mechanical forces, this and this are on the same line because the forces are, imagine, something like a spring or even gravitational force. It is between these 2 point masses, not, these are all point masses. So this and this are collinear on the same line. So again, the cross product would be zero. So all internal forces, they come in pair. And because of this, they would vanish. So for each internal force, I would have a counterpart in the opposite direction. And we have something like that. So all the internal forces in this summation would vanish. What is left would be the moment of the external forces. So for example, if I have one external force, would be the moment, R cross Fi, F external. F1 external, F2 external, all the F. So let's call that T. So let's call that total torque, all right? This is T, or you can call it M, sometimes moments. So this is all the torque that it is applied on that rigid body. Then minus that. So I can write this. T equals to, or sigma T, or M moments equals to H dot C plus MR of G with respect to C cross AC. So we have total moments of forces, external forces, equals to the rate of change of angular momentum around point C plus this term. Now, this term can be zero in 3 cases. Right? What are those cases? So let's write it here. One of them is that this is zero. The other one is that this is zero. The other one is that these two are parallel. Again, cross product would vanish. So when this is zero, it means that G and C are the same. So if G and C are the same, then R from C to G, the location of G would be on top of C. So RGC would be zero. So the case one would be G is C. So we write total moment equals to the rate of change of angular momentum around center of mass. So we can write T or sigma M equals to H dot of that center of mass, around center of mass. All right. The other case is that when AC is 0, so we pick a point and we write angular momentum around that point, for which that point is going with constant velocity. Constant velocity makes the acceleration 0. Rarely we see constant velocity except when that velocity is 0, meaning that that c doesn't change. Anyway, it's like, for example, when we have a pendulum, right? Something like that. So when we have that point C is constant, right? The acceleration of that point C is 0. So that is the case that we usually encounter. We write it around the stationary point, but generally it can be not stationary, but with constant velocity. But say that, okay, this is 0. This means usually stationary point, but bear in mind that it doesn't have to be. It can go with constant velocity, all right? So if this whole thing is on a truck and that is going with constant velocity, still I can use that point C to write uh, that. And the third case is that RGC is parallel to AC, or in other words, this is RGC, right? This is that vector. So if the acceleration of point C is toward that line, either the acceleration of point C is along that line going toward G or in the opposite direction, then still it would work because the cross product would be 0. You might think that what are those cases? Well, the only case that we might encounter in mechanical engineering is that when we have a disk rolling without slipping, all right? In that case, without slipping, rolling without slipping, and with uniform disk, because if it rolls without slipping, the acceleration of this point is toward that geometric center. So this is point C, and this is, let's say, geometric center. Let's call it O, all right? If geometric center is the same as the center of mass, because the acceleration is toward the geometric center, again, when we have a disk that rolls without slipping, then the acceleration of this point, because if you think about it, the motion of that point is something like that. So the acceleration is toward that center. So if this is a uniform disk, then O and G are the same, all right? Then the acceleration of point C would be toward G, meaning that this, which is that line, and the acceleration of that point C, which is along that line, are parallel, so this would vanish. Again, we can write the total moments, I mean torques, moments of forces around that point C equals to the rate of change of angular momentum around that point C. Don't forget that, again, the geometric center, it is toward the geometric center of a disk, and the geometric center and the center of mass should be the same. Otherwise, this doesn't hold true. For example, let's say I have a disk that some part of that is hollowed out, or it is some other material, all right? Then the center of mass, if this is hollowed out, the center of mass is a little bit off center along that direction. There are more masses there. Then again, then this won't hold because it is again, like before, it is the acceleration is toward the geometric center because the way it moves kinematically, I mean, in the way the geometric of the motion won't change, but the center of mass is off center. So I would suggest that pick. So this is the last case, is parallel to AC, all right? I would suggest that use these two cases to be safe and forget about this case. Although I have a video that I solve a problem with this case as well. So I would say that you can forget about that if you write total moments or moments of forces, torques around the center of mass equals to the rate of change of angular momentum around center of mass or a stationary point. You can use both. We will see that for 2D systems, this would be I omega. For 2D system, this would be simplified as I omega because this is, you see, omega cross r. I would have r cross omega cross r. Then that can be written as I, which is mr square, all sigma of mr square. So it would be I omega. And the derivative of that would be I alpha for 2D systems. And this would be a number. This would be a vector. All right. But for 3D system, this would be a tensor. This would be a matrix 3 by 3. Again, that is the topic of another video that I have in my channel. So for now, the rate of change of the angular momentum around the center of mass or around the stationary point equals to the total moments of the external forces or total torque on that rigid body. All right. Thank you.